DeBrino, and my project focuses on the effect of the knockdown of two proteins in addition to the knockdown of two proteins in conjunction with clinically used medication in order to investigate their impact on non-small cell lung cancer cell pathway. Lung cancer is the leading cause of cancer-related deaths, with non-small cell lung cancer accounting for 80 to 85% of all cases. Many environmental factors can contribute to the development of this disease, however, it's most often correlated with cigarette smoking. After patients are diagnosed with non-small cell lung cancer, they are often diagnosed for EGFR and ALK sensitizing mutations. While we usually think of mutations as harmful for our health, in this instance they are actually beneficial because they allow for the use of targeted treatment approaches to be used. The two drugs used in targeted treatment include crizotinib and erlotinib. Crizotinib on its own shuts down most of the cancer cell pathways, however, not all of them. Conversely, erlotinib shuts down very few things and actually makes the cancer slightly worse. However, when they're used together, these drugs are able to actively combat this cancer. However, we don't know why this happens or where the interaction takes place. My project focused on the knockdown of two proteins, ERF1 and MAPK3, in order to investigate if their knockdown and their knockdown in conjunction with the drug would be able to have a significant impact on the phosphorylation seen in non-small cell lung cancer. This led me to my questions. My first question is, what is the effect of the knockdown of the ERF1 protein? As this protein is a negative regulator of EGFR, I believe that PERK levels would increase. My second question was, what is the effect of the knockdown of ERF1 as well as crizotinib being added to the condition? And I believe that PERK levels would increase, and as crizotinib is a MET inhibitor, MET levels would decrease. For my third question, I asked, what is the effect of the knockdown of MAPK3? And as this is involved in intracellular signaling and is synonymous with PERK1, I believe that PERK1 levels would decrease and PERK2 levels would decrease. And in my fourth question, when the MAPK3 protein was decreased and the crizotinib was added, I believed that PMET levels would decrease, PERK1 levels would decrease, and PERK2 levels would increase. In order to measure this, I started my procedure. The feeding, growing, and splitting portion of the cells is basic cell maintenance to ensure that the cells are healthy enough for transfection to take place. The transfection stage of my experiment included adding siRNAs in order to knock down the specific proteins that I wished to investigate the impact of. In addition, crizotinib was added to the conditions in order to investigate the synergistic effects. When a cell receives a signal, the phosphorus travels down the pathway in order to reach its various goal. The phosphorylation measured indicates that if a greater phosphorylation is measured, the cell pathway is working, and decreased phosphorylation level indicate that the pathway is not working, which is desired when trying to combat this drug. In order to visualize this, a Western blot was run, including running gels, transferring, and blocking with various primary and secondary antibodies in order to gain visualizable results. The comparison figure 1 indicates the difference between the control and the ERF1 knockdown. In the ERF1 knockdown, it can be seen that PERK1, PERK2, and PRAD40 are completely absent, and compared to the control, the PMET levels are decreased. The second comparison between the control knockdown and the ERF1 knockdown in the presence of crizotinib indicates that PMET levels were even further decreased, and while there is a slight uptake in PRAD40, there is still an absence of both PERK1 and PERK2. The final comparison indicates the results of the phosphorylation on the ERF1 knockdown and the ERF1 knockdown in the context of crizotinib, indicating that there was very little relative phosphorylation measured, indicating further that the cell had a very difficult time functioning with this knockdown. This comparison compares the control knockdown in addition to the control and the MAPK3 knockdown. The MAPK3 knockdown shows an increase in PERK2 levels as well as an increase in PMET levels, as there are two bands noticed, and a decrease in PERK1 and both PRAD40 levels. The second comparison indicates the presence of the knockdown of the control in addition to the knockdown of MAPK3 in the presence of crizotinib, and the MAPK3 indicating that as compared, there's a similar PMET levels observed, slight uptake in PRAD40, and a decrease in PERK2 and intake of PERK1. When compared side by side, it can be seen that with crizotinib, there's less PMET observed, however there's a greater observation of PERK1 and PRAD40, indicating that overall, as a lot of relative phosphorylation is seen, the knockdown of this protein did not have a significant effect on the cell's ability to function. The results of my experiment do not support the hypothesis that if the ERF1 protein is knocked down, the PERK levels will increase, as PERK is completely absent from both conditions. In addition, it slightly supports my second hypothesis because while PERK levels were not seen, PMET levels were seen as decreasing. In addition, for my third hypothesis, the results of my experiment support the hypothesis as PERK2 levels were seen as increased. Also, for my fourth hypothesis, the results did support them because PERK2 was seen slightly greater as compared to the control, and PMET levels were further decreased when compared with itself. An alternative error that may have occurred in my experiment includes the complete amount of shutdown of each protein was not noted because we did not test specifically for it. For future experiments related to this project, it is potential that more types of mutations involving non-small cell lung cancer can be investigated. Much like our basic knowledge of SARS and MERS are aiding immunologists today to try to develop vaccines as we battle the global pandemic of COVID-19 by understanding basically where the interactions of the drugs and the immune system take place. We're able to create a map in order to put our funding into the places where the cells can have the greatest impact in order to fight this disease.